2.5 Graphing Rational Functions, Day 1. These are going to be the steps for you to refer to when you graph these. We're also going to talk about some additional information on when to find asymptotes and when to find vertical asymptotes. Let's go ahead and jump into our first example. So for our first example, as you can see, we're going to have several steps to complete this graph. Here's what these letters stand for, and they are in order to be able to graph this with a fair amount of time being saved. The first thing we're going to do is factor. The second thing we're going to do is find any holes or removable discontinuities. This V stands for vertical asymptotes, which of course are infinite discontinuities. This second H stands for perhaps a horizontal asymptote, and we're going to do some analysis to determine whether a horizontal asymptote exists. We are going to have x-intercepts that will still have multiplicity and behavior similar to polynomials. We're going to find the y-intercept. The G stands for actually going to graph this, and then we're going to talk about the domain. Let's get started. So the first thing that we're going to do is we're going to factor. So we're going to factor the numerator and the denominator. The denominator seems pretty low level. I do not have an a value in the front. I'm going to go ahead and factor the denominator. So the denominator is going to turn into x plus 2 times x plus 1. For the numerator, I am going to slide and divide. I'll just show my work right here. So for the numerator, 3 times 4 is 12, and we want it to add to a 7. That's going to be 3 times 4. We're going to go ahead and divide by that front number. So my first factor that I see is going to be x plus 1. And the other factor that I see is going to be 3x plus 4. Now what we're going to do is we are going to find a hole. And we absolutely have a hole because I have factors here that cancel. When we are working through this, I am still going to use a red pen for any discontinuities. So I am going to use this to show that these are going to cancel out. So with my red pen, I cancel these out, and then I immediately go to the blank for my hole, and I write the opposite value in here. This was a plus 1. So I'm going to plug in a negative 1 into the reduced fraction. So we're going to go ahead and wipe out these x plus 1s, and everything else that remains is going to look like this. 3x plus 4 over x plus 2. So we're going to plot this hole, but that's just an x-intercept. So we're going to go ahead and find the, x-coordinate. We're going to go ahead and find the y-coordinate by plugging negative 1 into this fraction. So when I plug in a negative 1, it's going to be 3 times negative 1 plus 4 over a negative 1 plus 2. So 3 times negative 1 is negative 3 plus 4, and then when we clean up this denominator, that's just going to be a positive 1. So a negative 3 and a positive 4 is going to give me a y-coordinate of a positive 1. Okay, moving on, I'm going to go ahead and keep my red pen because the next step is going to be a vertical asymptote. Vertical asymptotes always come from the bottom. It is your restriction. So if I try to solve this for the value of x right now, I would state that x could not equal negative 2. That is going to be a vertical asymptote when we graph it. Any restrictions in the denominator become vertical asymptotes. So let's go ahead and state we have a vertical asymptote at x equals, and it is the opposite, negative 2. Now, before I put my red pen down, just like x-intercepts, vertical asymptotes also have behavior. So we know this behavior either is tangent, straight, or concave, T, C, C, or S. This behavior is very similar to end behavior of a polynomial. A behavior of an asymptote is either going to be the same or the opposite. And the rules apply just like it does for an end behavior of a polynomial. So if I look at just this little baby expression down here where I found the restriction, notice that this exponent is understood to be a 1. So this piece, just the denominator, has an exponent of 1. 1 is odd. So this vertical asymptote is going to have opposite behavior. And I'm always going to make a note of that because when I go to graph it, I don't have to search through my work. As you can see, we have several steps. All right, factor, check. Pole, found it. Vertical asymptote, we determined it from the bottom. Now we're going to talk about the horizontal asymptote. And that's the degree phi. So determining what to do if there is a horizontal asymptote, I am going to look at this piece right here. When you determine if there is a horizontal asymptote or not, we always go back to the original equation. Now, if there are more degrees in the denominator, if the denominator wins the degree phi, whoever has the most denominators or the most exponents is going to win the fight. If the denominator wins, then the horizontal asymptote is always y equals 0, which is the x-axis. If there's a draw where the denominator and the numerator have the same degree, then we're going to just divide the leading coefficient. And if the numerator wins, we are going to have an oblique or a slanted. It's going to have a slope. It's going to look like a line with a slope. So let's go ahead and go back to our problem. All right, here we go. Remember, this is the only time we really look at the original equation. Here we go right here. The top is a degree of 2. Remember, it's in standard form. The bottom is a degree of 2. That is a draw. Nobody wins the degree phi. So we're just going to divide the leading coefficients, the numbers in front. The front number is a 3. The bottom number down here is understood to be a 1. 3 divided by 1, that's going to be your horizontal asymptote. Horizontal lines start with y. 3 is going to be the answer because that is how we divided the leading coefficients.